Hello and welcome to NHP's webinar on hazardous area fundamentals. My name is Krajinovic and I'm a commercial engineer for NHP Electrical Engineering, specializing in safety, sensing and hazardous area equipment. So this will be just the first in a series of webinars created specifically to inform you on hazardous area environments, equipment and practices according to AS/NZS 60079 standards, or the hazardous area standards. So just first off, you will see in the window there to the right that there is a Q&A section box, and you're more than welcome to post any questions that you have at any time during the presentation, as these will likely be answered as we go through the presentation by our support staff, but we'll also have some time at the end of this presentation to address any of these questions that you have during and after. So in this session, we'll be exploring what makes up a hazardous area, the explosive nature of materials, and how material properties are grouped to aid selection of hazardous area equipment based on certification and marking. So what we'll cover today will be an overview of the fundamentals of hazardous areas. So there'll be some level of detail, however, it's just important to note that although you will not learn everything in today's session, you will have a better understanding and appreciation of what is involved with hazardous areas and equipment selection afterwards. So this presentation will cover what is a hazardous area, where they are, and we'll quickly go into who's responsible for identifying these. Then we'll go over explosive atmospheres of gases, vapors, and dusts, and what conditions are required for these explosive atmospheres to occur, followed by covering flammable materials, and we'll talk about how they behave, which can give rise to an explosive atmosphere. And then we'll move on to the properties of gases, vapors, mists, and dusts, and just talk about the properties of these materials that can affect the likelihood of combustion. Then after that, we're going through some material grouping, which is just effectively how we group the large number of properties, and we'll see that that helps us later in product selection. And then we'll follow that with temperature classes, zone classifications, equipment protection levels, which are again more groupings to help understand the requirements of hazardous areas and aid in product selection. Then after that, last two things we'll cover the types of protection methods. So what protection methods effectively are available for use in hazardous areas. And we'll go through certification and marking. So what's required here and how to read these effectively. Now, many liquids, gases, and dusts which are processed, handled, and stored in industry are combustible and may become explosive given the right conditions. So flammable gases, liquids, vapors, or combustible mists and dusts mixed with air in the right proportions form what is known as an explosive atmosphere. Now, hazardous areas exist in many industries, from petrochemical to chemical, handling and storage, sewage treatment plants, and food processing and handling. And also hazardous areas often occur in premises that are frequented by the public, with the most obvious one being a petrol station. Now, just quickly, in terms of whose responsibility it is to classify a hazardous area, according to AS/NZS 3000, clause 7.7.2.1, this responsibility rests with the person or parties in control of the installation. So this requirement, or the requirements for this classification, are contained within the hazardous area standards, and that's the 60079.10.1, which is for gas and vapors, and .10.2 for combustible dusts. So these just detail how to classify the area and give you some examples. Now, the important thing to note here, however, is this does not mean that the person or parties in control are expected to perform the classification themselves, but they're obligated to identify the potential for a hazardous area and engage a competent individual to assist. And again, it's just important to note that according to AS 3000 and 60079.14, all electrical equipment used in a hazardous area must be certified for use according to these standards. So it's just important, I guess, to be aware of this. Let us now look at what is required for an explosive environment when gases and vapors are present. So generally, an explosion can occur only when three elements are present. That's explosive material or fuel, oxygen, and a source of ignition. So the explosive material may be any flammable or combustible substance and could be in the form of a gas, a liquid, a vapor, mist, or dust fibers or flyings. So it must be present in sufficient quantities and must be mixed with sufficient quantities of oxygen to form an explosive mixture. And the ignition source must have sufficient energy to ignite the explosive mixture. So it must have enough energy within the spark, or heat energy, or no explosion will occur. Now, for most flammable and combustible materials, these conditions are often referred to as the fire triangle or combustion triangle that you can see here. And the video here just shows what happens when you take away one of the thirds of the triangle. So with the lid on, there's no combustion as you don't have any oxygen. And just so you know, the flammable liquid here is being heated up to its auto ignition temperature. And obviously when the oxygen is present in the right proportions, you then have combustion. So now looking at what's required to have an explosive environment when dusts or dust fibers and flyings are present. So for combustible dusts, the dust pentagon applies. So not only is there an ignition source and oxygen supply, there is also fuel in the forms of a combustible dust layer. Now these are fuels that may become airborne later. And then there's also airborne dust that has been dispersed and airborne dust that is confined. The video on the right has a drum filled with wood shavings, a flare in the middle, and a bottle of compressed air underneath. So if the wood shavings were ignited without being dispersed, they would still burn, but very slowly, as only a small portion of the surface area is exposed to the air. But when the compressed air is released and the dust is dispersed into the air, this increases the surface area. And then this increases, obviously, the amount of oxygen in the mix, and then you have combustion, as we can see. So to give you more of an idea of flammable materials, which may lead to an explosive atmosphere, so there's various types of flammable materials we need to look out for. And each of them have different sets of properties which can affect how easily they can form an explosive atmosphere. Now, these are defined in the standards, but we'll go through them quickly. So flammable liquids, they're called this as they have a flash point, which we'll go through in a little bit. And they're materials like petrol, acetone, and paint thinners. Now, with flammable liquids as well, they give off vapors through evaporation, and these can be quite flammable, and you need to look out for those as well. Then we have flammable gases. So these are obvious things like hydrogen, methane, or natural gases. And we also have flammable mists, which are droplets of liquid that are dispersed in the air, such as aerosols. And an example of this would be spray paint. Going on to dusts, with combustible dusts, these are mostly organic, but there are some metals and minerals that are included in here. So these will be things like grain, sugar, wood, coal, and aluminium dusts. And then continuing on with dusts, we also have fibers, which include cotton, wool, nylon, and polyester, and flyings, which are things like sawdust and lint. And these are mostly waste particles due to processes. Now, going into a bit more detail, the differences between gases, vapors, and mists. So the important thing to note is that not all gases are lighter than air. Some, like propane, are heavier than air and will pool in low areas such as troughs and ditches. Vapors in sufficient quantities also do not always occur at normal temperatures, but can increase as the temperature increases. So an example of this is diesel and kerosene, and its vapors are not necessarily combustible at room temperature, but if you raise the temperature to over 80 degrees, it will ignite if you put a match to it. However, if you spray these two out of a spray bottle, you turn it into a mist, and the small droplets have much greater surface area, so they give off more vapor at room temperature and will become combustible. Now, just a little bit more on the properties. So first off, flash points. So this is the lowest temperature at which a material gives off enough vapor to form an explosive gas-air mixture immediately above the surface. Now, this points to the likelihood of flammable atmosphere existing at a given temperature. And as you know, if you have a material with a flash point and ambient temperatures around here, this material will be giving off additional vapors. So there's a higher likelihood of atmosphere existing. Now the video to the right of flashpoint is an example of this, but the flame is not sustained as the sample is not hot enough and not enough vapors are being given off. So this material in this case would be close to the flashpoint there. Then we have ignition temperature, and this is the minimum temperature at which a flammable substance will ignite and sustain combustion without an ignition source. So if the material is hot enough itself, it will spontaneously ignite, which is known as the auto ignition temperature. But it's just important to note that the fire triangle still applies here, so, as we saw before. So if you don't have oxygen, then you wouldn't have ignition. And it's important to note as well, a direct result of having an established ignition temperature is the limitation of surface temperatures of equipment within hazardous areas. And the last one here we've got is minimum ignition energy. So this is just the minimum energy in joules required to ignite a flammable substance. So it's effectively a certain amount of energy is required for an explosion to occur. If the energy is less than this in a spark, then no explosion will occur. Also, a smaller energy requirement for an explosion to occur effectively means that the material is more volatile. And the video on the right here just shows a box with a flammable gas or vapor in it with the correct mixture. And once you introduce a small spark with the minimum energy, you have ignition. So a surprising amount of dusts are combustible, which you might not have considered. So milk powder, flour, and sugar. So these are all things you would find at home, and they are combustible, but they just can't auto-ignite. They need to follow a few basic rules before they can be capable of causing an explosion. So firstly, they must be combustible, which about 75% of man-made dusts are. There must be an ignition source with enough energy. The dust must be capable of being airborne or kicked up into a cloud. The dust must be concentrated enough. The cloud must be contained in order to create enough pressure to warrant an explosion, and the air must contain enough oxygen to support and sustain the explosion. So there's a few more properties of dust to consider to determine how volatile they can be, with a few temperatures to be aware of. So first off, if a dust layer accumulates on a piece of equipment, this means you run the risk of the equipment overheating to the point of the dust igniting. And this is known as the layer ignition temperature. We also have when the dust is kicked up into the air and becomes airborne, there is a temperature at which this can also ignite, which is known as the cloud ignition temperature. So it's just important to note here that these two temperatures can be completely different and there's no relationship between the two. Lastly here though, we have the minimum cloud ignition energy, and obviously your source of ignition must have enough energy to ignite the dust as well. But with dust, there's a few more physical properties to consider. The particle size and shape, so the greater the surface area, the easier it will be to ignite. And you have to consider moisture too. The less moisture content, the more flammable the material is. There's also conductive and non-conductive dusts, which have their own properties that come into play when considering dust subgroups. So non-conductive dusts, like most plastics, can generate enough static charge to spark, which can ignite the explosive dust atmosphere. And then you have conductive dusts like metal shavings or filings, which can cause arcs and sparks when they come into contact with live parts or short tracks on the circuit board. Now, as you can see, there are a lot of different properties which affect the likelihood of a combustible material becoming an explosive hazard, and not all materials are alike. So it makes sense to split them up into groups, and this helps quite considerably when figuring out what sort of equipment we can put into these areas. So group one is for underground coal mining, and they have some very specific requirements, which we won't really cover today. In most cases, you will find sites which fall under groups 2 and 3 and their subgroups. So group 2 is for explosive gas atmospheres, and they split this then up into 3 subgroups in order of the amount of energy required to ignite the mixture. So you can see there, 2C is the most volatile with the lowest ignition energy of 18 microjoules, with 2A for things like propane and that requiring 260 microjoules. Then when we move on to group 3 here, so this is for explosive dust atmospheres, and they also have 3 subdivisions. So 3A is for flyings and fibers. And so remember, these are usually long strands of material like shavings of cotton wool or wood chips. And then you have 3B, which is for non-conductive dusts like the plastics we were talking about, and 3C, which is for conductive dusts. And just so you know, for reference, if you're unsure what grouping can be used within a gas, vapor, or dust subgroup, you can refer to 60079.14, clause 5.5, and this shows a table giving the relationship between these groups and subdivisions and what can be used. Now, along with the group of flammable material, we can also classify a temperature class. So this is a method of choosing equipment which remains below the ignition temperature of the surrounding explosive atmosphere. And these are split into 6 T ratings from 1 to 6 shown here. And they're effectively based on the maximum surface temperature the equipment can generate at a standard ambient of 40 degrees Celsius. And you can just see here, T1 is the highest, so this surface temperature would be 450 degrees, and T6 is the lowest, so the surface temperature would be 85 degrees. So if you have an environment where the explosive atmosphere has an ignition temperature of 120 degrees Celsius, you would need to select a piece of equipment that's either T5 or 6 rating, as these will not go above 100 and 85 respectively. So say you select a piece of equipment such as a light fitting, which has a T5 rating. This means you'd expect its surface temperature not to exceed 100 degrees, and that's provided it is being used in the correct ambient temperature ranges specified. And this means you could use this product within the explosive atmosphere which has the ignition temperature of 120 degrees Celsius. Now, for dusts in particular, there are special requirements according to 60079.14, clause 5.6.3, and you need to look at both the cloud ignition temperature and the layer ignition temperature. So here, to figure out the temperature that you need to take 2/3 of the cloud ignition temperature and compare it with the layer ignition temperature minus 75 degrees. So whichever of the two is lower, this is the temperature that you use when selecting a T rating for your equipment. But you just need to be careful. So with dust layers, this method only allows for a 5mm layer of dust. So you need to have regular housekeeping and cleaning to ensure that it doesn't exceed that level. So now we understand how much of a risk explosive atmospheres are with respect to their surroundings. And we particularly want to look at the probability or likelihood of an explosive mixture being present in an area and classify it. So these areas are based on the likelihood are called zones. Now there are 3 zones for gas and dust, not including the safe zone, of course. And for gas, they are zones 0, 1, and 2. So zone 0 is where the explosive gas mixture is continuously present or present for long periods under normal operation. So this is usually inside the vessel storing the gas, like a fuel tank. Then you have zone 1, which is where the gas mixture is likely to occur during normal operation, but only for short periods of time. And it's usually near a filling or release point of the vessel. And then we have finally zone 2, which is where the explosive gas mixture is not likely to occur during normal operation, but may exist for a short period of time if there is a fault. So this could be anything from a leaking joint or a flange or any kind of leak. And it's just important to note that the times that are shown there are just a rule of thumb, and they're by no means a strict figure. But if we look at that picture of the plane refueling, we actually have all 3 zones here. So you can see zone 2 is in the surrounding environment around the refueling truck. So that would only exist if there was a leak or a fault somewhere. Zone 1 is immediately then around the truck in close proximity, specifically around the refueling points and release of the fuel. And then you have zone 0, which you can't see within the tank properly, but that would effectively be within the fuel tank of the plane and the truck. So like gases, dusts have their own zones based on the same principles of likelihood. So zone 20 is where the dust is present continuously or for extended periods of time under normal operation. Zone 21 is where the dust is present for short periods of time during normal operation. And 22 is where the dust is only present for short periods of time during abnormal operation, or again, when there's a fault. Now, the image to the right here shows a series of grain silos with a conveyor on the top feeding into the silos, and there's emptying points underneath. And again, we have all three zones here. So you can see zone 22 surrounding the silos. So if there was any fault, you would expect the dust air mixture to be around here. Zone 21 would be in close proximity to the conveyor feeding grain and the emptying points underneath. And zone 20 would be within the conveyor itself and the silos. So zones go hand in hand with what is called equipment protection levels, or EPLs. Now this puts the piece of equipment into a group that says whether it can be used in a particular zone. So they start with G or D for gas or dust respectively, and have a second lowercase letter to indicate the protection level, either A, B, or C. So A is good for zone 0, B is good for zone 1, and C is good for zone 2. And the same for dust zones 20, 21, and 22 respectively, where A is good for zone 20 and C is good for zone 22. Now the EPLs are defined in 60079.0 clause 3.33, with the relationship between the EPL and the zone being shown in the standard 60079.14 clause 5.3. So if you want to put a piece of equipment into a zone 1 environment, it can use something that has an EPL of GB, which is suitable for zone 1 or 21, or GA, which is suitable for the higher likelihood zone, zone 0. GC in this case is only good for zone 2. In saying this, however, there are instances where you can put in equipment of a lower EPL into a more dangerous zone, but this involves doing a comprehensive risk assessment to ensure that the level of risk introduced is at an acceptable level, and there is a lot of documentation required to back this up and justification. But it's just important to note that this can be done if required. So we've covered off on what makes a hazardous area, as well as groupings and ratings. So now it just comes time to choose what type of equipment to put into a hazardous area. So when making your selection, you need to consider the following about your area. You need to consider the zone it's going into and the EPL of the equipment, the ignition temperature or your T rating, and the dust and gas group and subgroup. Now these are stated according to 60079.14 clauses 5.1. And importantly, it's important to note that any other environmental factors such as ambient temperature, corrosive environments, chemical exposure, and IP ratings, those sorts of things, would still need to be considered regardless, what you normally consider these. You still need to consider these within a hazardous area, and it's even more important than a non-hazardous area. And the reason for this is you wouldn't want to put, say, a polycarbonate light fitting into a room with some kind of chemical vapor that would effectively destroy the fitting, which would then void the protection method and potentially cause an explosive source of ignition. So there are various ways that a piece of equipment can be used in a hazardous area without the risk of igniting the explosive atmosphere. Now these various ways are known as the protection types, and there are many more than what you can see here, but these are the most common ones you will come across. So they're the ones we're going to go through today. Now there are dedicated standards for each of these protection methods which detail the requirements for the design, construction, and testing of the electrical equipment and EX components, but this is generally more for the manufacturers of the products. And just to note, other ones you don't see here, which you may see out in industry, is EXM for encapsulation, EXQ for powder field, and there's a few more. Now, EXD is a flameproof enclosure, so you don't want to confuse this with fire-rated enclosures, as they are two completely different things. So a flameproof enclosure is allowed to breathe, which means that the flammable mixture is able to penetrate and get in. If an explosion occurs inside the enclosure, it will prevent the explosion from getting out and igniting the surrounding atmosphere. And it does this by allowing the hot gases to escape out the sides through special flame paths, which are engraved along the threads and flanges of the product, and act to cool the gas down to below the ignition temperature using the material of the product to do this. So this is the most basic and oldest methods of protection, and it can be actually difficult to install and maintain, and is very heavy and bulky. But on the plus side, it allows you to use non-EX certified sparking equipment inside of it. So things like contactors and circuit breakers are okay to go in there. So because of this, they are very versatile, and they're still used in many applications. And they can be used in all gas zones except 0. So they're suitable for zones 1 and 2. Now, EXE works by avoiding an ignition source in the first place, and it does this by using equipment which doesn't produce arcs or sparks and limits the temperature of the enclosure. So it has additional strict measures for avoiding these conditions, such as the derating of terminals, having the correct clearances and creepages, and limiting the amount of heat generated by components inside the enclosure. Now, these are better than EXD in terms of maintenance and installation costs, and they're generally lightweight and easier to work with. However, you are limited to specifically using EX certified components inside. But like EXD, EXE is still good to go in all gas zones except 0, so it's good for zones 1 and 2. Now, EXN is for non-sparking, and it uses the same principles as EXE by avoiding the occurrence of it becoming a source of ignition. So they rely on the very low probability of an explosive atmosphere being present for a very short amount of time. So it's only actually really good for gas zone 2. Now, they are an alternative to EXE with the same benefits of being easy to install and maintain, and are also lightweight. However, again, you can only use specifically EX certified components in them, just like EXE. And again, these are only good for zone 2. Now, EXD, E, and N, the protection types that we discussed so far, are only useful for gas environments. So for dust, we use EXT, which is protection by enclosure or exclusion. Now, this method effectively just keeps the dust out, and they are often also specially designed so that dust layers can't form easily, and when they do, within certain limitations, they don't raise the surface temperature high enough to be a source of ignition. Now, dust protection has been known by various names over the years and has gone through several iterations with the updating of standards. So the old Oz EX standard was Dust Ignition Proof, or DIP. Then we had, with ANZ IEC, EXT with a capital D, which was under standard 61241.1. But this is now withdrawn with the new standard in favour of EXT with a little A, B or C, which is under 60079.31. The second letter after the EXT in this case is used to indicate the level of protection, with TA again being the highest, good for zone 20, TB second highest for zone 21, and TC for zone 22. Now, TB is what you most commonly find out in the market, so it's good for zones 21 and 22. I guess one thing, it's just after this, it's just important to note that you'll find a lot of equipment out there that's dual rated, so it's protected for both gas and dust. So you might find a piece of equipment that's EXTB rated for dust for zone 21, but also EXE rated. So it's just important to be aware of that. Now, last one we're going to cover today is EXI, which is intrinsic safety. And this is actually the safest form of protection. Now, it works on the basis of limiting the amount of energy available in the circuit, which could cause a spark. It is one of the few protection methods which can be used in zone 0 and zone 20. And so EXI equipment is often used with an intrinsically safe barrier or isolator, which sits either in the safe area or within a hazardous area rated enclosure. Now, this barrier limits the voltage, the current, and the power output to the field device, so it cannot produce a spark large enough to ignite the explosive atmosphere. They also often have multiple layers of redundancy, so can handle one or more faults and still perform their function as needed. They are only for low powered devices, so this is important. So like sensors and instrumentation. So the amount of energy in EXI circuit is far too low to be of use in many other applications. Typically it's 24 volts or lower, with very low currents in terms of milliamps or microamps. The great thing though is that EXI can be used. You can use non-certified simple apparatus in the field and keep it safe. So this would be things like push buttons, switches, thermistors, limit switches, pretty much anything that doesn't store energy or has a very low and known capacitance and inductance. So for example, you could put a regular non-EX push button station in a hazardous area via an intrinsically safe barrier and not have to worry about having to get an EXE or D enclosure system and follow all the special requirements for glands, cabling and maintenance, etc. So despite the extra expense of the barrier, it can actually be much cheaper overall to use a simple apparatus instead. But it's just important to note you still need to perform your entity calculations to make sure with the cable runs you have and everything that you have a safe system. Now, all EX certified equipment will have a certificate of conformity, and the end user or end users will need this certificate as part of their hazardous area verification dossier on site. The IEC certificate number is printed on all certified equipment and is made up of a few bits of information. So you can see there, first you have IEC EX. So this is the certificate or certification that's accepted for use within Australia. Following that, you have what's printed UL in this case, which is the certificate issuing body or the test house. Now there are other test bodies like TUV, IMQ, there's a number of them, but effectively they're just a test house that issue the certificate. After that, you have the year of issue, which is 13. So in this case, it is for 2013. And then you have the job number, which in this case is 0049. So this is saying this is the 49th certificate that has been issued within 2013 by the test house UL. Sometimes you'll find another letter at the end of the certificate number, so either an X or a U, which indicates that there's specific conditions of use and that the equipment within this certification is a component only and must be used with other EX equipment to be fully certified. So conditions are listed in the certificate and are like installation requirements, and you must follow these. So you would find this on, say, a push button or terminal designed for use within an EXE enclosure. Now, all the necessary information is in the IEC EX Certificate of Conformity, and luckily these can be downloaded online for free from the IEC EX website that you can see written there. Now, generally all you need is the certificate number and you can start browsing through the certificates. So on the EX equipment itself, you'll find the appropriate marking as well. So this marking needs to feature some important information about the EX protection type of the equipment and is verified by an inspector once and after it is installed and in use. So on the label, you have the protection method for the gas group, the dust group, and the subgroup, the EPL, temperature class, and IP ratings, along with the certificate number. You also have some other info you may find there that would be like the serial number of the product, the manufacturer's logo, and any special warning labels like you must isolate elsewhere before opening. So if we just take note at that middle section of the certification there where it says EXD to CGB, we'll break this down further on the next slide. So on this label, there's two sets of marking. which means this product is dual certified with two protection methods, as I was mentioning, is possible before. So if we break this down one by one, the first part is just saying EX, so it's effectively telling you that it has some form of EX protection. The next letter is the protection type. So on the top line, we have D, which is for flameproof enclosures that we covered. And on the bottom line, we have TB, which is protection by enclosure, which is for dust environments. Now, after this, we have the material group. So 2C on the top line is for gas, and this is saying it's suitable for the most volatile gas. So it's good for all gas groups and all types of gases. Now, the second line, 3C, is telling us that it's good for conductive dusts, which also means then it's good for non-conductive dusts and flyings as well, or groups 3B and 3A. Then we have the EPL after that. So GB on the top line, so G is for gas, and the B tells us it's good for zone 1, and that means it's also good for use in zone 2. DB on the bottom line is for dust with the D, and then again, this is saying with B that it's good for zones 21, and of course then 22 as well. Now, the next bit of information is a bit different for gas and dust. So in gas, we have the temperature class. So that's written as T4 there. So that's saying it's good for 135 degrees. But for the dust, it just has the temperature of 120 degrees Celsius. So if you remember, this is the lower temperature as a result of the testing procedures for the dust standards, where you have the 2/3 of the cloud ignition temperature and the layer ignition temperature -75 degrees. And then after this, you have the IP rating, which is 66 in this case. So now we know pretty much everything about what kind of hazardous area this product can go into just by looking at the equipment marking itself. So say we want to put this item in an area with methane, which has an ignition temperature of 537 degrees, and it's a zone 1 environment. Would you be able to use this item? So sure, if we look at the label, we can go through. So it has EXD protection, which is good for gas environments. Then we can see again, the group is 2C, so it's good for all gases. Following with the temperature class, we have T4, which is 135 degrees, as I was saying. So this surface temperature is much lower than the ignition temperature of the gas, so we can use that as well. And then lastly, if we look at the EPL, it's GB. So that's good for zone 1, as this was. So you'd effectively be able to use this item within that environment. So this concludes today's presentation on hazardous area fundamentals. By now, you should have a greater understanding on where hazardous areas exist and what is required for an explosive atmosphere to occur in both gas and dust atmospheres. You know, what properties of gases, vapors, mists, and dust can make it easier for material to undergo combustion. And you should have an appreciation on the various ratings given to hazardous area equipment, such as material grouping, T classes, zone classification, and EPLs, and how these can be used when selecting equipment for a hazardous area environment. So I'm now able to answer any questions that you may have sent in during the presentation.
Thanks very much, Tom. My name is Daniel Nathanson. I've been one of the moderators on this session. Just like to say thank you very much for the presentation, Tom. It's been very informative. So we have had quite a few questions come through, and we've endeavoured to answer as many of them as we can. But what we'll do is we'll give you some questions to answer, Tom, if you can. Yep. So we have one question here, which is, hang on, let me just go scroll down and find it again. So someone has asked, can I put my own products within one of your hazardous area rated products?
Okay, so with this, so you can't actually put one of your own products within one of our hazardous area rated products. So there's a number of things to consider. So when the enclosures are manufactured and put together, there's things in terms of spacing within the enclosure itself that you need to be aware of, and you can't kind of void and spacing and stuff like that. So effectively, in order to do that, you would need to check with us if it's one of our products and see if that is possible to do.
Great, thanks, Tom. We have another question here from Derek. He asks, is the diesel tank room for generators in a hospital, can it be considered a hazardous area, zone 1 or zone 2? Would the light fittings or any other electrical apparatus used in it need any EX protection techniques?
Okay, so yes, it is likely that that would be considered a hazardous area. So if you're not sure that it is one and there hasn't been a classification that's been done, you would need to go and seek someone to classify the area and make sure. But effectively, as I was saying through the presentation, there's the classification standards. So in this case, it'd be 60079.10.1 to cover gas and vapors. And it would have a lot of examples there, especially towards the appendices, which would have pretty much that example that you would be able to find. But you would definitely need to get the environment classified first, and more than likely it would be either a zone 1 or zone 2 environment, and you would need light fittings that have that or suitable for that zone.
Great stuff, thanks, Tom. There have been quite a few questions around the use of ATEX equipment. Would you mind maybe clearing up whether or not we can use ATEX in Australia?
Okay, so there's a few conditions on that. So first off, it's effectively no. So if you have if there are suitable products that exist that provide the same protection and function, then you need to use ones that are IEC rated effectively. The only way you can use an ATEX product within Australia is if one of those products with the IEC rating doesn't exist, in which case then you're allowed to look at ATEX, but you would need to create a full effectively risk assessment report and make sure that the product is suitable for that environment, that application, and you'd need to create what's known as a conformity assessment document, which would then be put within the hazardous area verification dossier, just justifying and explaining why you've selected that piece of equipment.
Excellent, thanks a lot, Tom. We've got a few more minutes left for questions. So we have another question from Uli. Asks, if the instrument is in contact with the gas, would we need EXI rated equipment?
So not necessarily. So it depends what the instrument is. If it's hazardous area rated and it's a zone 1 and it's suitable for use in zone 1, then it's okay. The most cases, if the sensor itself is EXI rated, you would need to use it with a barrier in that case. That's how it achieves its protection effectively. But if it was something else like EXD rated, which there are some unique EXD rated sensors and stuff, and it's suitable for zone 1, then it would be able to be used in that environment as long as you follow all the conditions around its certification.
Thanks, Tom. We have another question. Can I modify hazardous area equipment myself? That is, can I add another bung to a pre-engineered enclosure?
So no modifications can be made. So this includes, like I was saying before, addition of new items inside the enclosure or new entries or anything like that. So all of this needs to be checked and verified by the manufacturer to make sure that the enclosure is still going to provide the protection that it's meant to provide. So, you wouldn't just be able to drill holes anywhere that you need because it might weaken the material itself. So no, you wouldn't be able to do anything like that. If you did have one of our products, you could ask us to see if it's possible, and then we would likely have to verify that and then do that for you.
Thanks, Tom. I think one final question, or in this case, it's a comment. So Robin has mentioned, also when selecting EX devices, you need to know what you're doing and being appropriately trained to do it. Otherwise, you can purchase the incorrect gear. Tom, do you have any further comment on this one?
Yes, that is correct. So to work within a hazardous area, you need to be what's deemed as a competent individual. And I know within the standards, there's they do mention, what makes up a competent individual. And this includes things like going through training courses, for instance, classification and design, installation and maintenance courses, as well as a number of other things. But yes, that is true. You do need to be a competent, what's deemed as a competent individual to work within a hazardous area environment.
Fantastic, Tom. Thank you. That should be all the questions for today. Again, thank you very much for the presentation, Tom. Incredibly informative.
All right, thanks, Dan. So thanks for the questions, and thank you all for joining this webinar. I hope you found it beneficial, and if you'd like to watch it again, a recording will be uploaded to the NHP YouTube channel shortly. If you have any further questions about hazardous area fundamentals, please contact your local NHP sales representative. And with smarter and faster decision making and seamless connectivity spurring new collaboration, NHP is enabling the connected enterprise. See you next time.